Thanks for calling in. Today I'm going to talk about Turbine, a stream processing service management platform we built at Facebook. Most of you probably know what stream processing is. To help everyone understand today's talk a bit better, I will do a very quick intro. In the database world, we have data stored in storage, and the user will submit lots of queries to the database to get results. On the other hand, in stream processing, we have an infinite amount of data, and we have a fixed query to process the data and generate the output in real time. For today's talk, there are a few important properties of stream processing that's worth mentioning. First, we need to process the data all the time. Second, we have a very tight latency budget, often on the order of tens of seconds. Third, the amount of data we got can vary quite a bit from time to time. We'll see how those requirements have a big impact on why we designed Turbine in the way we did. In today's talk, we'll use Scuba as an example. Scuba is a real-time analytics system at Facebook, and it is used for real-time ad hoc analysis of arbitrary data. For example, site reliability engineers watch server errors by using Scuba. When an error occurs, they can pinpoint whether it is due to a bug in a particular endpoint, a service in a particular data center, or some physical issue with part of a data center. As you can imagine, latency is quite important here. Let's take a quick look at how Scuba works. On the input side, we have Scribe. Scribe is a message bus system widely used at Facebook. It's like Kafka. For site reliability example we mentioned earlier, machine will log relevant information into Scribe. Then stream processing jobs will process those information, annotate them with dimension data, such as data center, rack ID, and then load those data into Scuba. Once the data is available in storage, user will be able to run arbitrary queries against them. In today's talk, we use the Scuba Tailor as a running example. The purpose of Scuba Tailor is to continuously ingest data into Scuba storage. As we mentioned earlier, the latency is quite important for Scuba. After data is logged into Scribe, it should show up in Scuba storage within tens of seconds. Each Tailor job ingests data for one particular Scuba table. A typical service level objective here is the P99 latency should be less than 90 seconds. Those jobs by themselves are pretty simple. They just deserialize the data, convert them into the proper format, and write them into Scuba storage. But they run at a big scale. On the diagram to the right, you can see the throughput and the number of tasks for Scuba Tailor as a whole. Peak ingestion throughput for Scuba is on the order of hundreds of gigabytes, and the number of tasks are on the order of 100K. Those requirements are common for all stream processing jobs. So those challenges are: one, very strict and service level objective. So typically P99 latency on the order of tens of seconds. And we need to satisfy those SLOs, assuming machine failures and large amount of traffic variations for the input data. The second challenge is we're running at large scale. So we have tens of thousands of machines, hundreds of gigabytes of data per second, and several thousand distinct stream processing applications. And Scuba Tailor is just one such application. Now, let's take a look at the high-level diagram of Turbine. At high level, there are three big components here: job management, task management, and the resource management. Job management stores the job information. When user authors a query, the resulting job information will be stored in the job store. Job management also handles complex job updates. We'll talk about the details here a little bit later. Task management then gets a list of detailed task information from the job store and schedules those tasks. It also performs load balancing. Due to the time limit, we won't be able to go into the details here. Please look at the details in the paper. The resource management layer is responsible for dynamically adjusting the resource allocation to the jobs. It also has a global view of the whole system, so it can make cluster-level decisions. In addition to the user, Turbine also takes on-call as first-class citizen. The on-call can override decisions made by those automation systems. In today's talk, we'll mainly cover portions of the job management and the resource management. For the rest of the talk, we'll focus on one particular problem: how many tasks we should launch to process data for a particular Scuba table. This problem is trivial when we only have a few jobs to deal with, but for a service with hundreds of thousands of tasks, this can be very challenging. For example, who decides how many tasks we should have? How to update the number of tasks safely? How do we satisfy the 90 seconds SLO when the load can vary a lot? We'll look into the details of those problems and see how we solve them. So the first problem we want to take a detailed look at is who decides how many tasks we should have. There can be many decision makers here. First, we have user. User can provide some initial guesses. For example, here user can say the number of tasks should be equal to the amount of partitions we have in the input scribe category. Then there's autoscaler. Scaler automatically decides the task count based on various factors, and we'll look into the details about autoscaler a bit later. And finally, there are on-calls. And in fact, there can be multiple on-calls: user on-call and service on-call. And all those actions can happen at the same time. How do we reason about this? Do we want to apply those changes in the order of the time those actions were performed? In that case, on-call might not have a chance against autoscaler. The scaler runs all the time. So should we stop the scaler if on-call wants to make some manual overrides? Obviously, that's not very desirable. To solve those problems, we developed a hierarchical job config system. Here we have 4 levels of configs. First is a base config. It defines a collection of common settings like package name, version number, checkpoints, directory. So here we typically don't set the number of tasks here, and this is usually set by the info developer. Then we have the provisional configuration. It is set when user creates or updates the application. Here we set the number of tasks to be the number of partitions we have in the input stream. The scaler config is updated by the autoscaler whenever it decides to adjust a job's resource allocation based on the workload and the current resource usage. Finally, the on-call config is used by on-call when human intervention is needed to solve an ongoing service problem. Those configs are exactly the same format, and they are ordered by priorities. On-call config has highest priority. We can also set expiration time for the on-call overrides if needed. Each actor will update their corresponding config, and the final job spec is generated on the fly. We'll take a look at how they will be used a little bit later. Now we know the number of tasks. How do we update the jobs to the right number of tasks? First, let's take a look at the steps we need to update the task count for a job. First, we need to stop the existing jobs. Then we need to wait for the stop to finish. And we will redistribute the checkpoints to match the new task count. And we'll start the new jobs with the new task count. Finally, we'll wait for the whole thing to finish. Now let's see what can go wrong. We already mentioned there are many actors for the system. If 2 on-calls are updating the job at the same time, we might corrupt the checkpoint. What if in the middle of process, failure happened? Can we make sure the system is left in a consistent state and is able to recover by itself? To solve those problems mentioned earlier, we'll have 2 tables in the jobs.db. First is the expected job table. It stores the hierarchical config we mentioned earlier, This is where all actors write their modification to. The second table is a running job table. This table contains the running job config. It is a source of truth for task management system. Then we introduce a state sinker to reconcile the difference between the expected jobs and the running jobs. If the task count in the expected table doesn't really match the running task count, the state sinker will perform the lengthy transition steps we mentioned earlier. When those transition steps are done, state sinker will commit the new job config into the running job table. And we also make sure the transition steps are important, and the final write to the job table is the commit point. Finally, let's take a look at how we provide 90 seconds SLO when the input data volume can vary a lot. In this chart, we show the input rate for one job. The peak time input is about 50% higher than the valley time, and sometimes there can be sudden spikes. Obviously, we cannot count on humans to react to those kind of load changes. To solve those problems, we'll need autoscaler. We mentioned the autoscaler a bit earlier. Now let's take a detailed look. Autoscaler has a few building blocks. First, it has a symptom detector. It will look at various metrics and decide if we need to make adjustments. For example, it can look at the lack of stream processing jobs. If we encountered an SO violation or about to have violation, the autoscaler can take action. One possible action is to increase the number of tasks for the job. Plan generator will take the input from the symptom detector and figure out the new plan with help from the resource estimator and pattern analyzer. The resource estimator will estimate the usage of resource for a given job. This information is then combined with the historical traffic patterns to generate the actual plan. Now let's take a detailed look at the estimation for the task count. Here is a basic formula on how we estimate the number of tasks we need. It's basically the amount of data we expect to consume divided by the processing rate of each task. If currently we have lags, lag recovery time will also be taken into account. The interesting parameter here are the input rate and the estimated processing rate. For the input rate X, it's a combination of both the current input rate and historical pattern. For example, if we know the current input rate is 5 GB, and we know in 1 hour it will be 6 GB based on historical pattern, we will then just use 6 GB. Obviously, the amount of time we look ahead is configurable. For the estimated processing rate, typically for a particular job, it's predictable. So for a newly provisioned job, we'll measure the processing rate during the canary time. Once it's running in production, we'll continue to monitor the progress and adjust the value properly. For example, if we have a lagging job, then the observed processing rate will be a good indicator for the peak processing rate. Now, we have, here's one example showing the scaler in action for a particular SCUBA table. Here we have a job which was stopped for a few days due to user error. Once the user fixed the problem, there's a large amount of lag to process. And the scaler was able to quickly scale the job to 128 tasks, and it churns through all the lags very quickly. Here's another example showing how scaler deals with data center level events. Here we have a storm starting in the morning of day 2. And in day 2, we got quite a bit more traffic. Scaler was able to increase the total amount of tasks to deal with the increased traffic. When the storm ends, the amount of tasks was adjusted back to the normal level. Okay, that's all I'm able to cover in today's presentation. And please check out our papers for a lot more details. Thank you.